Today we're talking a little bit about more about quaternions and their properties. So the idea today is that we know how to manipulate them a little bit better beyond the usual definition, so that we know a few properties, so we get a little bit more comfortable on how to operate them, especially to understand much better how they can be used for decoding rotations. So first of all, we are going to start with the question of Quaternion commutativity. And that will be a question. We will ask ourselves, I'm not telling you if quaternions are commutative or not. I'm asking you if a quaternion P times a Q, if that's the same thing for all quaternions, if that's the same thing of the product inverse. So that is a question. We want to analyze if this is true or false for every single quaternion, if we can do that all the time. We know that's true for complex numbers. We know that's true for real numbers. But quaternions has some additional structure, and we don't know that. So we gotta check. And notice that checking that is the same thing as checking if P times Q minus Q times P, if this is always equal to 0, okay, for whatever P and Q we choose. That's why I put this special symbol over here. And the way we are going to go around that is to just recall what was the definition of a product. So if we get a P times a Q, what we are going to do is the P0 times Q0 minus P dot product Q. I'm using this notation over here for the product. And for the three other components, we have something like this, as you might recall from the previous lecture. And then we do minus, but the order inverse, so inverse everything. Now we get Q0 times P plus P0 times Q plus Q times P. And this product here, as you might recall, is the cross product. And we're going to solve that. Notice that for the first line, we have that those two are commutative, so they cancel out. This minus this is 0. The dot product is commutative, so those numbers, they're the same. So in the end of the day, this minus this is equal indeed to 0. Now this one is a little bit more interesting, because you have P0 here, Q P0 here, so they will cancel out. Those two, they will cancel out. And those two, on the other hand, recall that the cross product, it's not commutative. So this term right here is equal to minus P times Q. Just as a small recall, you can check this geometrically, that if you have a cross product of two vectors, you will usually do the right-hand rule from one for the first to the second, and that's the direction of the product. And if you invert that order, this right-hand rule will invert, and what you will get is the same vector, but the order reversed. So this is what we get. And in the end, when we do this term minus that term, you had that twice of this term over here. So you have 2P cross product Q. And this guy over here is not identically 0. If you do have two quaternions that P and Q, this complex part per se, they are aligned, if they are parallel, yes, you will have quaternions that commute, but not in general. So we will say that quaternion product is not commutative. Okay, so first thing to know that this answer is a no. They are not commutative. And this breaks the structure that we have from real and complex, that we cannot do this. Keep this in mind now, that we are not allowed to do that operation. We also want to know, it will be interesting for us to know some properties regarding the norm of the product. Okay, so the norm of the product, what we want to know now is if quaternion P, product quaternion Q, if this is always equal to P times q. And we want to know if that's true. I mean, not that's true. Yes, we want to know if this is true or not. So notice that this is a quaternion product. So you're doing a product between two quaternions, and then you're taking the norm. So here you get a real number. The result is a real number of a quaternion product. And here you have the norm of a quaternion. So this is a real number. This is a real number as well. And then you do a real product. Okay, so this product is different than that one. And you want to know if you can do that. If you can just take the product out like that. And the way we do this is that we can just compute that. So I will compute this one time so that we get a feel of the manipulation of quaternions. And then later for the other properties, we will just go quicker. I will invite you to do them yourself. But as you will see, it's just algebra. But for us to feel more confident about this, let's check that out. Let's see if we compute that, what that is. And for that matter, I just want you to recall this product here is this norm is the Euclidean norm, okay, of a vector. So you can say that if you remind I could write this, the Euclidean norm I could write as a dot product of two vectors, or in matrix form. If I choose a basis, I can say that this transpose is equal to that. So all of that are different ways of writing up the square of this guy. And I'm going to do that because in the end I want to work with this. So what I'm going to compute is P quaternion product times Q. And what we will get then is, we want to do the square so that I can use that. So we get P0 Q0 minus P. It's the same formula of this one, right? It's just the product. And having this, but I want the norm of this guy over here. Therefore, I'll do the transpose of this guy times this same guy again. So let's copy it over here. And what we have now, this is a transpose times another vector. So the product of this will be this first term times this first term, plus the transpose of that times the second term. So the transpose times this is a number, and then what we will have is a P0 Q0 squared plus, notice that you have this one times this one minus this one times this one, therefore minus 2 times this part plus this one is squared. So that one is squared. Notice that this is the transpose times that. So this is really the norm of the dot product. And the norm of the dot product, we can write it as a where theta is the angle between both of them. So this is the norm is squared. So what we have here is the squared of those terms, right? And now we go and we compute those other guys. So it's the transpose of this times that. So I'll do the transpose of the first. Q transpose times all of that. Second term, transpose times all of that. Third term, transpose. So it's the transpose of this. Times all of that. And now let's analyze each one of those terms, because some of them will cancel out and I want to tell you exactly which ones. First of all, we have a this one over here, P0, Q0. We can see that it's exactly this term over here. So we'll have that one of these will cancel with this term, and the other one will cancel with this term right here. So you can see that Q0, P0, and then P transpose Q is the dot product. So this two will cancel out with this one. All right? Another thing that we can see is that here, P cross product Q will generate a vector which is orthogonal to both P and Q, and therefore is orthogonal to Q. So when you get a vector which is orthogonal to Q and do a dot product with itself, it will cancel out, not with itself. With you have a product that is orthogonal to Q. When you do dot product with Q, what you get is 0, right? Because the dot product of orthogonal vectors is 0. Therefore, this term here will be 0 as well. For the similar reason, this term here will also be 0. This is orthogonal to P. When you do dot product with P, will become 0. What you get here, same reason. You will cancel this out and this out. All of those guys cancels for orthogonality. And what you have here in the end will be this term over here. I will rewrite it. Okay, so the dot instead of having the transpose times the vector itself, you will remember that that is equal to the norm squared. And the norm of a cross product will be, so this last part here, then just the last part, okay, is equal to the norm of the cross vector, which is P, Q, and in this time is the sine of the angle between them, right? This is the norm of the cross vector, but this is the norm squared. So we have 2, 2, and 2. And then I want you to notice that those terms added, since you have cosine squared plus sine squared, they will equal to 1. So really this cancel out with that, and what remains is just this term over here. So overall, what remains is P0 Q0 square plus this term over here, which is P squared Q, plus this one, which will be P0 squared times the norm squared of Q, plus Q0 squared, so the Q0 squared times P squared. And finally, we can, for instance, here, let's put P0, those two terms together. So you will see that P0 squared is equal to Q0 squared plus the norm of Q squared. Okay, so those two terms become this one. And this over here, I'll put P, I'll put perhaps P squared. I'll put them together by means of the P squared. So what we'll have is Q squared plus Q0 squared. And notice that finally this term over here, this is the norm of Q, this is the norm of the quaternion squared, and this is the norm of the quaternion squared too. So we can put those together. And when we do that, we have that what remains is P squared plus norm of P. And then what we have is finally Q squared, and this is the norm of P. So what I have is that. Notice that indeed what we have in the very end is that the norm of the quaternion product is equal, the square of the norm is equal to the square of the products. You can take the square root of both sides, and you will see that for this case, this is true. So this one is a yes, we do have that. Okay, and that will become very useful for us when we are talking about rotations. Finally, the other property that we want to know is if it is associative, meaning if we have P times Q times R quaternions, if that is always equal to P times Q times R. And this, you can already imagine, this was quite tedious. Therefore, we don't want to do that a lot of times, so we'll just tell you the answer. But it is nevertheless a good exercise to go through this yourself. So you can go through the algebra yourself, but I will tell you the answer. The answer is yes, that actually it is true. Okay, and I let you check that by yourself. Another thing that I want to talk about is the Quaternion Inverse. So the Quaternion Inverse is similar to what we had with the complexes number. So remember here for the complex, as a remark, for a complex number Z, for every complex number which was not zero, for every non-zero complex number, we could build the following number. We would take the conjugate of Z divided by the norm square, and this would generate an inverse, right? Remembering that the conjugate of a complex number, if the complex number was AB, the conjugate would become A minus B. So you would compute this, which was the complex conjugate, you would divide it by its norm squared, and that, if you multiply it by Z, you would get 1. So really the complex inverse is that number that when you multiply by Z, what you get is 1. 1 is a real number, but in a complex sense, this is 1, 0, right? But they are the same thing. So this is what we had, and we want to know if we have the same thing for quaternions. If for a given quaternion, we say that it has we say that A inverse of a quaternion is a quaternion such that when you multiply it by the right and multiply it by the left, you get 1. And this one is written in quaternion form as 1, 0, 0, 0, right? You have that. So the question that we have is, does every quaternion have that? So we know that every complex have that. Does every quaternion have it too? And if it does, is it unique, or do you have several? Those are important questions for us. And what I want then to define, so we can tackle that, is what we call the quaternion conjugate, which will be quite easy to remember because it's exactly the same idea. So you take a quaternion, and to conjugate it, so I will use this symbol over here, you just repeat the real part, and the imaginary part again, like that, we will take just the negative of it. So we'll do this kind of by definition. I will define this as the conjugate, and I will show you that this formula works. So let's try this one over here, for instance. Take that one. Take any quaternion, written generally as this. Do the product with the inverse. I'm proposing an inverse, all right? So we need to check if that's actually an inverse or not. I'm proposing that. So we need to do this product, and if it's 1, that's good. I know that that's an inverse for the quaternion. So what we have over here is that, when I want to do this, I want to remember that we want to do exactly the same thing. So I will divide it also by the norm of the quaternion. Okay, so this is what I will propose. And therefore, if I'm proposing dividing by quaternions, norms, you don't want to divide it by 0. So again, I'm assuming that this quaternion is not the 0 quaternion. Okay? So given any non-zero quaternion, I can do that. And if you go through this using the same formula, you will have that this is Q0 squared minus Q times Q. There's a minus here, so in the end this becomes a plus. Now, for the second part, we will have this times that, you have this minus that goes over there, plus Q0 times Q, and then you add their cross products. So this is by definition, by computation, and what we get from here, we can see that this, again, is the norm squared. And these guys over here, what you get is that, cancel with this, and a cross product of a vector with itself is also 0, so all of those, sorry. This is those, they cancel each other. This is 0, and what we will have here then is the 0 vector. And when we divide this by the quaternion norm, we have that those cancel out, and we will have 1, 0, which is indeed equal to 1. So what we did is that we did find a computation rule to find A inverse, right? So we know how to compute inverses of quaternions now, and we want to know if it's unique, or if there's another vector that I could multiply it, and I could also find 1. So imagine for one moment that there are two vectors, Q1 and Q2, that are inverses of Q, of a given Q, okay? So if that's the case, you can say that, that Q1 is equal to Q1 times 1, right? This is the identity. If you multiply by 1, you get the quaternion back. 1 can be written as Q times Q2, because this, because I said that Q2 is an inverse, so that's one fancy way of writing 1. Then what you have here by the associative law is that Q1 times Q times Q. So this must be the same. And finally, this one by being an inverse as well, this is another fancy way of writing 1. So this is always 1, and therefore 1 times Q2 is Q2. So if you do have two inverses, you can show that actually the first inverse is equal to the second, and the inverse is unique. And in the next step is now using all those properties to come together with a rule to decoding rotation. And I will do next time, but until next time, goodbye.